We're very happy today to have Giorgos Kotsovolis from right here in Princeton talking about base note spectra of binary forms. Go ahead.
Okay, thanks a lot for the invitation. It's great to be speaking here at the Institute. Okay, so to start, I want to define the basic object that we're going to be speaking about today, which is this base note spectra in the Euclidean setting. So assume we have a polynomial that is homogeneous in k variables of degree n. Homogeneous simply means that the sum of these exponents is equal to some fixed number n, and we take our polynomial to be real. So to each such polynomial, we can associate a corresponding differential operator as follows. We can simply substitute the variables and change them into differentials. So for example, if I have a sum of two cubes, I have the Laplace cube. Okay, and the question we're interested in asking is, for any k-dimensional unimodular lattice, unimodular here means that it has volume 1, this operator acts on the C-infinity functions of the Euclidean torus Rk mod lambda that have mean 0. And what we want to understand is the first eigenvalue for this action. Okay, so this is a spectral problem, but it turns out that it has a very nice interpretation in the geometry of numbers. Because, for example, if we take our lattice to be the integer lattice, we can see that the exponentials are very easily seen to be eigenfunctions. So the eigenvalues themselves are simply these scalar multiples of the polynomial evaluated at the vectors of the lattice. So when we're looking at the first eigenvalue, we're essentially looking at the smallest value our polynomial attains at the vectors of the lattice. And this is not true just for the integer lattice, this is true for every lattice. So if dp is acting on the functions of the torus Rk mod lambda, the eigenvalues are equal to 2 pi to the n multiplied by the polynomial evaluated at the vectors of the dual lattice. So to understand the lambda 1 eigenvalue, we have to understand this problem in the geometry of numbers of what is the shortest vector with respect to the polynomial. It's not really the shortest because it's not a norm, but yeah. So a central program in the geometry of numbers is Mahler's program, which is for such a polynomial p, we want to understand not just one lambda 1 eigenvalue, we want to understand what the lambda 1 eigenvalue could be. We want to understand the set of lambda 1 eigenvalues as a whole. It is a global object. We're not simply looking at one of the tori. We're looking at all of the tori together, and we're taking the set of the lambda 1 eigenvalues. Maybe I should write this definition because it will be a central definition for the talk. Okay. And I should say that Mahler did not define this as the base note spectrum. The name base note spectrum comes from Sarnak's recent interpretation of this problem as an instance of the base note spectrum problem. Sarnak defined this for general lambda 1 eigenvalues of operators on finite volume portions of symmetric spaces, but here we have the Euclidean setting of this problem. Okay. So what do we know about the spectrum a priori? We just know that it's a subset of the non-negative numbers. That's all that we know. So a first thing to observe is that obviously this eigenvalue, this infimum, is smaller than the value of p evaluated at the shortest vector. And the shortest vector goes to 0 as lambda escapes to the cusp of a cell k by definition. So this is just by continuity of the polynomial p. So this forces 0 to always be a limit point of the spectrum. And also that the spectrum of p is bounded because the polynomial is continuous and at a neighborhood of the cusp, it goes very close to 0. Okay, so it's a bounded set. What else do we know? So regarding the right part, the upper part of the spectrum, this function going from the lattice to this lambda 1 eigenvalue is easily shown to be upper semi-continuous. So what we obtain from that is that the spectrum always attains its maximum. So it might be open on the left, it might not contain 0, but it always contains its maximum. Okay, are there any questions so far about the definitions?
Right, you've used Mahler compactness, which
Yes.
you sort of said was obvious, but
Okay, yeah, so, no, okay,
that happens to be a theorem.
right, okay, so the fact that near the cusp, the shortest vector.
Defines the, that is a, defines a defines a boundary is Mahler compactness. In other words, you have to show that you, if that number is bounded below, then you are in a compact set.
Yeah. Right, so I'm gonna now go into some examples to better illustrate what the spectrum can look like, what the spectrum is in various cases. So let's start with the simplest in structure, at least, example, which is the sum of squares. So if P is the sum of squares, what we're looking at is literally the square of the shortest vector. And this is a continuous problem because if you shift your lattice by a little bit, the shortest vector of the lattice also shifts by a little bit, which means that we might not know what the spectrum is exactly, but at least we know that it's an interval by continuity. It's an interval from 0 because as lambda goes to the cusp, we go close to 0, and up to some gamma k, which is Hermite's constant for the lattice packing problem. So in this case, it's an interval. Let's look at the next case, which is P being an indefinite quadratic form in at least 3 variables. So in this case, we have Oppenheim's conjecture, which is a theorem due to Margulis, which states essentially that the infimum of P over lattice is non-zero if and only for some A matrix representing the lattice, we have that the composition of P with A is a scalar multiple of an integer polynomial. Okay, so to evaluate the spectrum in this case, we only have to care about these multiples of integer polynomials, because otherwise a quadratic form will represent things arbitrarily close to 0, so the infimum will be 0. Okay, so we have to restrict to this integer polynomials, and using the Hasse principle, we can show that the spectrum is a sequence converging to 0. So for example, if we have at least 5 variables, we know that integer polynomials represent everything. So the infimum will be exactly 0, and in fact, the spectrum of P will be only the point 0, nothing else. But also for 3 and 4, we know that it's a sequence going down to 0. Okay, so we see some diversity here. The spectrum can be a sequence going to 0, it can be an interval. Let's look at one more example. So if P is the product of the coordinates of the lattice vector, the first thing to observe is that this polynomial is invariant under the diagonal action, which means that if we take the infimum of this polynomial over lattice, this is invariant under the diagonal orbit of the lattice. And this means that the spectrum is related to the heights of the diagonal orbits on SLKR mod SLKZ. So there's a conjecture in this area, one of the most important conjectures, which is the Margulis conjecture, which states that for dimensions 3 and more, any diagonal orbit is either unbounded or it's compact and comes from a totally real number field of degree k. So if we knew this conjecture, which is a very big if, we would also know the Littlewood conjecture, we would know that the spectrum is a sequence converging down to 0. Okay. So these are the examples that I'm going to talk about, that I did talk about. I'm not going to talk about them anymore. So the spectrum is a very easy problem to state, the baseline spectrum problem, but we don't really know many cases. You see that even this case is extremely conjectural. So for the rest of the talk, I'm going to focus on 2 variables. I'm just going to talk about binary forms, which is the very first unsolved case. Because if we just have one variable, a homogeneous polynomial of one variable, we all know what its infimum is over the integers. Okay, so We're going to discuss Mahler's program for k is equal to 2. So we fix P to be a binary form of degree n and discriminant dp. So in this case, for any matrix A, B, C, D you might choose, if we take this conjugation, the standard conjugation composition, sorry, of P with A, this is also a binary form. And if we take our matrix A to have determinant 1, the discriminant of the binary form will be the same as the discriminant I started. Okay? And by definition, the infimum over the integers of the new form will be the infimum of the previous form over the associated lattice. What I'm trying to say here is that when we're looking at the base note spectrum, we're looking at the infimum of the polynomial over lattices, but then another way to view this problem is that looking at the infimum over the integers of all the polynomials in the SL2 orbit. Okay, this is a simpler formulation. And this SL2 orbit is a subset of all binary forms of the same discriminant and the same degree. So what we have is that the spectrum, which is a set we want to understand, is a subset of all the infima of the polynomials of the same discriminant and degree. This is a much bigger set. This is essentially the union of all the spectrum. Okay, but for binary forms, it is not hard to see that these sets turn out to be equal for degrees 1, 2, and 3. And this is just because the SL2 has dimension 3. So another way to state this is that all binary cubic forms, for example, are GL2R equivalent as long as their discriminant has the same sign. Okay. Okay, so I'm now going to start going up with binary forms. I'm going to discuss linear binary forms, quadratic binary forms, and then in the end, I'm going to get to what I actually want to discuss today, which is binary cubic forms and binary forms of higher degrees and what we know there, which is not a lot. So if P is linear, the problem is quite easy. So if P is linear, the spectrum is just a point 0. And why is that? So it suffices to show that the infimum of such a linear form over the integers is 0. And you can see that if you divide by y and a, you can bring this really in the form of Dirichlet's theorem in the Fontane approximation. If you choose R to be equal to minus b over a in this theorem, you'll see that for this infimum, you'll get a saving of a y. And since you have infinitely many rationals x comma y satisfying this inequality, you can choose y to go to infinity and this infimum will always be 0. So the spectrum of linear forms is always equal to 0. And moving on to the case of quadratic forms, the first thing to observe is that the base note spectrum problem behaves very well under scalar multiplication. If we understand the spectrum of P, we understand the spectrum of 6P. So we can assume that the discriminant is either 0, -1, or 1. If the discriminant is 0, the problem just goes back to the linear case and the spectrum is again just 0. If the discriminant is -1, we have already discussed that in the first example, because every quadratic form of discriminant -1 is GL2R equivalent to the sum of 2 squares. And this is again the lattice packing problem in dimension 2. We said that this is an interval because it's a continuous problem. And the spectrum is open 0 to square root of 1 over 3. With the extremal polynomial or the extremal lattice essentially being the triangle lattice. And the last case is when the discriminant is at 1. So this is the most complicated case in the quadratic cases. This is called the Markoff spectrum. Here just take spec of xy because again, all quadratic forms of discriminant 1 are the same. This is called the Markoff spectrum. In the literature, on the internet, Wikipedia, whatever, you usually find it like this. You usually see that it's a set of infima of binary quadratic forms of discriminant 1. Okay, and let's see what we know about the spectrum. Okay, are there any questions first? Okay, so when a form has discriminant 1, it has two real roots, distinct, row 1 and row 2. And what we're trying to understand is the infimum over the integers. So one thing you can see is that if one of these roots is rational, so if R is A over B, for example, you can just choose X to be A and Y to be B, and the infimum is instantly 0. So one could think that, okay, maybe the spectrum is just a point 0 again. Maybe this infimum is always 0 for binary quadratic forms of indefinite ones. That's wrong, sorry. But this is actually wrong. So a very simple counterexample. Let's use this form right here. You can see, first of all, it's an integer form, and it doesn't represent 0, which means that its infimum is at least 1. And for y is equal to 0, x is equal to 1, it represents 1. So its infimum is exactly 1. And since its discriminant is equal to 5, what we have proved is that 1 over square root of 5 is in the Markov spectrum. This was first proved by Hurwitz, and it would be just a random example of a number in the Markov spectrum, but it turns out that this is the largest number in the Markov spectrum. So we have Markov's theorem that 1 over square root of 5 is the largest point of M. And then the amazing thing is that there is a second largest point. There is a spectral gap, 1 over square root of 8. And then there is a third largest point, fourth largest point, and this keeps going. If you're trying to understand what these numbers are, where they're coming from the famous Markov equation. So there's this equation, sum of 3 squares is equal to 3xyz. If you take any triple xyz solving this of integers, and you take any of these coordinates, call it m, then m over square root of 9m squared minus 4 is a point of the Markov spectrum. And these are exactly the points of the Markov spectrum, above 1/3. And this is exactly what Markov did. So he classifies all the points of the Markov spectrum that are larger than 1/3. So unlike the cases that we saw before in the examples, this is the first case we see that is not an interval and it's not a sequence going down to 0, because it contains a sequence going down to 1/3. Okay, so we completely understand now what's going on with the Markov spectrum above the point 1/3, but what's going on lower in the spectrum? What's going on near 0? So there's a famous theorem of Marshall-Hall, which states that it actually contains an interval near 0. There is a constant c such that the interval 0 to c is inside the spectrum. And you might be wondering, what is this c? What is this mysterious number? And this was actually classified by Freiman, who showed that this c is equal to this hideous number. This is the largest interval in the Markov spectrum. This cannot be improved. This is optimal. What I can say maybe is that this number is about 1/5, probably. It's around 0.22. Okay. So I'm now done with the quadratic case. So if you want to ask about anything about the Markov spectrum, now is the time. I'm going to be moving to the cubic case.
What happens between C and 1/3?
Right, that's a very good question. So there's a lot of active research there, actually. This is a very hot topic, and has been for around 80 years. There's a lot of
Maybe warm is a bit.
yeah, warm, okay. Not cold, yeah. So there's a lot of fractal phenomena going on. This is related to the distribution of heights of closed geodesics on the modular surface. The way people usually study the Markov spectrum is with continued fractions. And there are still intervals inside there. There's intervals between this C and the Freiman constant, but there's also a very bizarre fractal phenomenon going on.
This particular number having an interesting continued fraction expansion.
Not really. I know it's continued fractionalized, but it's numbers. I don't know.
Where did this number come from? Looks ridiculous. Where did it come from?
All right, that's a very good question. It's actually very hard to find Freiman's original paper, it turns out. I've tried for a long enough time. You can find it in Russian, but I don't speak Russian. He does. Okay. All right, so
Wait, but, so what kind of behavior needs do you expect, like, you said there are intervals, but are there like pieces where it's not an interval, but it's like dense or something?
there's what? It's not as well, it's very badly structured. It's not a bunch of intervals going around. There's I think the following happens that you can find for any possible Hausdorff dimension, you can find an interval where you achieve this Hausdorff dimension. I think this is true, yes. Yeah, so it's a very bizarre set. Okay. Now let's talk about binary cubic forms. So binary cubic forms are this expression right here. And again, what we're interested in is that what could the infimum of such form be over the integers? And we still have this duality. So instead of taking the polynomial and taking infima over every lattice, what you can do is pick your favorite lattice to be the integers and look at the infima of all binary cubic forms over that lattice. So you can either choose to run the polynomials or the lattice. Both are acceptable. Okay, so in the 1940s, Mordell had a series of papers along with Davenport, very important on the distribution and the geometry of binary cubic forms. So let's start with this form right here, P minus. So this form, x cubed minus xy squared minus y cubed, is an integer form. Again, it does not represent 0, it represents 1, so we know that its infimum is 1. I have normalized this form just so that it has a unit discriminant, and what we have is that the infimum is this number, 4th root of 1 over 23. So the amazing theorem that Mordell was able to prove is that this is an extremal form. You can't do any better than this. If you choose any binary cubic form of discriminant minus 1, the infimum is at most this number. And for an intuition why this could be happening, so 23 is the smallest discriminant of a complex cubic field. Okay, and for positive discriminant, he took the smallest discriminant, which is 49 for totally real cubic fields. This is its form, x squared plus x cubed plus x squared y minus 2x y squared minus y cubed. And again, it's very easy to see that the infimum of this form is this 4th root of 1 over 49. Maybe you want to say that this is 1 over square root of 7. It is, but I just want to be consistent with the 4th roots. And again, he proved that this is extremal. If you take any binary cubic form of positive discriminant, you can't do better than this. This is as high as the infimum can go. And he proceeded making the following conjectures. He said that just like the Markoff spectrum, we should have a spectral gap. If this infimum is not exactly 4th root of 1 over 23, it should jump down. Actually, he made a more precise conjecture. He exactly said the number here should be the second largest discriminant of a number field. And he made the corresponding conjecture for positive discriminant as well. Maybe I won't go into the reasons of why he made these conjectures. You could see it as a generalization of the Markoff spectrum. This is a little bit naive. I think that historically based, he made these conjectures because of certain results of Davenport related to some spectral gaps close to the regarding the Littlewood conjecture. Maybe I will go back to this if I have some time, but since I don't have a lot right now, I will move into Davenport's results. So a few months after Mordell made this conjecture, Davenport was able to disprove this. So Davenport showed he was able to construct for every epsilon positive, he was able to construct a unimodular lattice lambda epsilon, such that the infimum of this form over lattice lambda epsilon is exactly there at the top. It's not the extremal lattice, but it's also not far from the extremal lattice. So Davenport disproved Mordell's conjectures, and he also disproved it for the positive discriminant case. So a theorem that I want to talk about today is that, quite contrary to this conjecture, what is actually true is that the spectrum of binary cubic forms are a whole interval. Not only there is no gap, but it's actually everything. And the same is true for positive discriminant. Now, these theorems might look the same, but I should say that this is much easier than this one. Okay. And now for the next 30 minutes, I would like to, probably for the next 10 minutes, I would like to go over the proof of these statements. And then I want to talk about binary n forms. Okay, so we'll start with the first one. What happens in the case of discriminant -1? So what does negative discriminant mean? It just means that you have one real root and two complex roots. So if we factorize it like this, we have one real root row and a ZZ bar conjugate complex roots. So the way to show that the interval is everything here is to isolate the problem, to forget about the real root, and to isolate the problem to the complex roots. So we define the set of unimodular matrices that fix the real root. So along this orbit, along this two-dimensional orbit, our polynomial looks like this. We have fixed row, and z lambda is now just a variable. And this way we have isolated the problems. It really looks like the binary quadratic case, the definite binary quadratic case now. And it actually turns out that the function going from lambda to the infimum over lambda for this orbit is a continuous function. And this is because the minimizing x and y's in this scenario have nothing to do with rho because we have fixed it. They only care about the relative size of z, which is a continuous function. So since we have a continuous function, it is very easy to obtain an interval this way. There are some details that I am forgetting here, but I want to talk more about the positive discriminant case because it's much more important, and it's more important for what's going to be happening in the n-ic case. So in this case, we have three real roots. No matter what curve you choose, no matter what polynomial you choose, when you compose with P, you'll have to move the roots because SL2 is three-dimensional. So there's no way you compose and you fix all the roots because in that case, your matrix will be one of 6 matrices, just a S3 group fixing this form. Okay, so how do we deal with this? So in order to study the infimum of this form, we have to find x and y such that at least one of these parentheses is small, right? So one of these parentheses should beat the y to the cube factor. So in order to beat with a y to the cube, we need to understand when we can approximate a number cubically well. So this is rational approximation, but with the exponent 3 instead of the exponent 2. And traditionally, the way we study this problem is with continued fractions, which I'm not really going to talk about, but I'm going to define them briefly. So every number can be written in this form, where the first number is an integer and everything else is a natural number. And if we stop this process at any point, what we obtained is a rational number, Pn over Qn, which is called a convergent of this number rho. And why convergents are important is because they fully explain the Davenport approximation of rho. So what we have is that a rational number x over y can approximate my number rho if and only quadratically well, if and only if it is a convergent. But in our problem, we're not just asking for quadratic approximation, we're asking about cubic approximation, which is much more. So what we're really asking, how this translates into the language of continued fractions, is that not only x over y has to be a convergent, but an plus 1, which is the first coefficient that doesn't appear here, should be very big. It should be bigger than this denominator. And this denominator grows at least exponentially. This is a very large number. So we very rarely have cubic approximation is the point of this. Even in the case of the Fibonacci number, so the golden ratio, which is the slowest growing continued fraction expansion, it's still exponential. So these numbers are very, very big, very, very fast. Okay, so how do we prove that we have a whole spectral interval for a positive discriminant? So we have a form like this, and just for convenience, we restrict to the family of matrices that fix the last two roots. We don't do this for any mathematical smart reason. We just want to isolate the problem to only one of the roots. This is not really offering anything. Okay, so this is a curve because we have wasted 2 dimensions to fix 2 of the roots, and we have 1 more dimension to play with. So this is essentially a curve. And on this orbit, we have that P composed with these matrices has this form. So 2 fixed roots, and 1 of the root became a variable. So just like before, notice that if this variable becomes a rational number, this infimum is immediately 0. And it's not just 0, it is 0, but it's also achieved. It's a minimum, and it's hit by x and y to be the numerator and the denominator. So the idea that solves the problem here is that this property is almost locally stable around converges of row 1, which means, I will better explain the next slide, but it roughly means that if I go very close to a convergent, if I go very close to some a over b that's a convergent of row 1, with very high probability, I am also minimized by the same a and b. To make that rigorous, if a over b is a convergent of row 1, and t is in this neighborhood right here, it's a cubic neighborhood, there's 3 cases. Either the infimum is also achieved by the same x and y, or it's achieved by x and y that might be large, but not too large. They're finite. Let's say something inside minus a million, million squared. And there is a third case that the infimum is not achieved in finite time, which means that it's actually an infimum and never a minimum, or it is achieved in finite time, but for very big x and y. So what we say is that it's either achieved by A and B, or much larger, or much smaller. There's a gap in some sense in what the possible scenarios are. And the reason we win is that the t's in the last 2 cases are little o of 1 of the size of the interval. So we find intervals such that there's a restriction of the curve on an almost full proportion subset of the curve such that we have continuity. So we have found a subset. This is it doesn't have intervals, this subset, but it is a subset of this set with measure very close to 1 over b cubed. Very close, I mean that it becomes almost exactly 1 over b cubed, as b is one of the denominators of the convergence over 1, and we pick better and better convergence. So we have found some interval with measure close to full, such that for the restriction of t inside this subset, the infimum is achieved by exactly a and b. And this is now a continuous family. And since we have continuity, almost continuity, by choosing better and better convergence, we have that the spectrum is almost everything. Okay. And how do we go to everything from almost everything? Well, there's this principle, similar considerations for the other two roots give us basically almost everything in three variables. And there's this principle in multidimensional analysis that there's a standard theorem of Steinhaus that if you have two sets of positive measure, A and B, then A plus B contains an interval. The same theorem here basically will give us that since we have full measure phenomena in three variables, we can obtain a full interval. Okay? Okay. So are there any questions about binary cubic forms and the case of positive discriminants?
Sorry, this lambda in this middle equation is just the measure of this.
Yes, sorry, exactly. This is no eigenvalue. Okay. If there are no more questions about binary cubic, I'll get to binary n. So for binary n, as far as I know, there weren't any results other than some bounds on how large the maximum can be, but nothing about the structure. And so the theorem I want to mainly talk about is the following, that the spectrum of any binary n-ic form of non-zero discriminant is also an interval. So this is the main theorem, and for the rest of the talk, I'm going to be talking about its proof. It shares some common elements with the case of the binary cubic forms, but it's quite more complicated. And the reason it's more complicated is because we don't have Mordell's here. Mordell gave us the extremal lattice, and we didn't really care about the extremal lattice. What we cared about was that it's an integer lattice. Because of somehow Rolf's theorem or Chua's theorem, integer polynomials, their roots, have very good Davenport properties, or very bad according to your school. And here we know nothing about the extremal lattice. And it was very important that we knew the Davenport properties of algebraic numbers to prove this theorem where we, the local stability theorem, where we said that either x and y should be a comma b or much smaller or much larger. This wouldn't work if we didn't know Mordell's forms. So yes, improving local stability was crucial that we knew what the form was. And here we don't. And even though we understand now that the spectrum is a full interval, I still have no idea what these forms are, what they look like, what their properties are. This is still widely open. So what do we do when we can't solve something? We can almost solve it. So the idea is to approximate these extremal forms by almost extremal forms whose properties are good. So what is an almost extremal form? An almost extremal lattice. It's exactly what you might expect. So for some lambda naught extremal lattice, an epsilon almost extremal lattice is something that is very close in the norm topology, but also it should be almost extremal. This means that its infimum should be very close to maximum. Okay.
So what do you mean by this norm?
I just mean that the lattices are very close. Take two representatives of they're very close. They're very close in the upper half plane.
Oh, okay, okay, just
A quotient about
Just yeah.
space of lattice.
Yeah, the space of lattice. Yeah, they're just close. This is a very easy condition to check. This is a hard one. This is a finite condition. This is a Davenport. And there is no really any reason why this should be an easier problem than the initial problems. Like, why do we know or expect extremal lattices to exist? For example, if Mordell's conjecture was true and there was a spectral gap, extremal lattices wouldn't exist. And this is actually the main part of the proof to show that it's an interval. Somehow, if you show that you don't have a spectral gap, to go from that to an interval, you can just use the machinery that was applied to the binary cubic case. Okay, so how do we show that we have almost extremal lattices? So the relevant set in this case is this B epsilon, which I will be calling. So you fix some row, some number, and you define B epsilon to be the set of numbers Z close to this row, epsilon close to this row, such that the Davenport properties of Z are not too much worse than those of rho. Okay. And in order to find an epsilon almost extremal with good Davenport properties, what one has to do is you have to find some matrix in SL2R such that when acting as a Mobius transformation, it sends rho I to be epsilon of rho I. Of course, it does that. But if we pick the identity, it would do that. But we're also asking that T over rho I should have Davenport exponent too. Davenport exponent, maybe I should define that. So the Davenport exponent rho is the infimum of the numbers S, that's that rho minus x over y is less than over y to the S, where infinitely many x and y's. Yes. For almost all numbers, this is equal to 2, but there is a lot of numbers when this is not the case. And let me explain why this step was trivial in the case of cubic forms, but it's actually hard in this case of hard forms. So say we start with 3 roots, row 1, row 2, row 3. And we find some numbers, row 1 prime, inside, and everyone see down here? B epsilon row 1 intersected by E2. E2 will be the numbers of Davenport exponent 2. Row 2 prime here, again in B epsilon, row 2 intersection E2, and row 3 prime here. Again, the correspondence. So for any 3 roots and any 3 other roots, we can find a matrix T in SL2R sending one to another. This is because SL2R is 3-dimensional, and for every 3 points, we can go to any 3 other points. So all Davenport essentially had to do to disprove Mordell was to show that these sets are non-empty. If they're non-empty, you can just find a matrix T to do that. But if there's a 4th root, by playing with the 3 first, you have already prescribed what the 4th root is doing. And there's a high chance this will not go to the epsilon row 4 intersection E2. And this is the main problem. So here there is a, let me call it measure theoretic hope. The first thing one might try to do, if you understand the situation, is to attempt to show that as you go closer and closer to a specific root, this B epsilon set becomes very dominant. It covers almost everything. It's very high density. Then you could use measure theory to make sure that, okay, if my form T is very close to the identity, this should happen deterministically. So the hope is that if you choose an interval, the length of the interval going to 0, the interval intersected by B epsilon rho over the length of the interval. This is 1. This is the hope. If this was true, we could resolve this. But this is not true. What is true is that the lower limit of this density is 0. The upper limit is 1, but the lower limit is 0. And the way to go around this issue is try to understand when it's 0 and when it's 1. Because, okay, we understand that it oscillates, this density between 0 and 1, but what actually happens is that it really wants to be 1. It spends much more time near 1 rather than 0. So we have the following theorem, which is a structural theorem for this set V epsilon. Pick any number row and positive parameters T1 and T2. So I urge you to think of T1 as very small, 1 over a million, and T2, TAF2, sorry. And TAF2 much smaller, 1 over a trillion. So the following happens. There exists some delta such that for every interval of small diameter, there's 2 scenarios. Either our measure theoretic hope is fine and we're saved. We have a lot of very good points, many B epsilon points. Or we can find a subinterval that is not too much smaller. This is still very small, you understand, it's over 1 over a million of the initial density, but we have a much higher density of B epsilon points. We have 1 over we have just 1 minus TAF2. And if we choose TAF2 to be much more than TAF1, we sort of win in density. Okay, so there's this sort of duality. Either we have many good points or we can zoom in and find even more good points. And now there is an algorithm that we need to implement to finish the existence of extremal lattice. So the algorithm is the following. What we want to do is we have 4 roots or n roots. The case of quartic case and any case is pretty much the same. And what we want to do is we want to find some matrix T such that it pushes all of the roots inside the corresponding B epsilon intersection de Fontaine exponent 2. And how do we do this? We choose for the delta that we just talked about, some very small interval around 1. We project it back under the Mobius transformation near the identity of SL2. So we have a very small ball near the identity element of SL2. And let's start with the first root, row 1. The projection of this ball near row 1 is an interval. It either satisfies case 1 or case 2 of the structure theorem. If it satisfies case 1, we have a lot of good points, we're fine. In this case, we do nothing. If it satisfies case 2, we find a subinterval, just like in the theorem. We pull it back again near the identity element of SL2, and we push it forward again to the Mobius transformation around 1. And we substitute the initial interval with this interval. So whatever happens, we have accommodated the first root. No matter what happens, we have a lot of good points near it. If you do this step at most n times, where n is the degree or the number of the roots, what will happen is that you will find an interval such that the push forward near all of the roots has very high probability of these B epsilon points. And so you can just intersect and find an intersection being non-empty. Okay. Are there any questions about the algorithm? I should say
about the main theorem. So you're proving that at the maximum, you will get the full interval in a small neighborhood of the maximum. You get a full interval in a small neighborhood of any point in the space of lattice.
right. So this interval might look like the intervals we had in the definite case, because you also had intervals. But in some sense, it's
The interval up to what it is So there's a maximum over that.
Yeah,
So it'll fill out from 0 up to whatever that maximum.
yeah,
is.
even if you look at an arbitrarily small neighborhood of the extremal lattice and you focus on the lattices in there, you will still see the entire spectrum. Which, for example, doesn't happen for definite forms. It doesn't happen for the lattice packing problem or for anything because it's continuity. Here, we have an interval because of chaos in some sense rather than continuity. Yes. All right, so maybe I should say here, in case this algorithm confused, that if you're in case 1 and you do nothing for the root row 1, then after you go to root row 2 and possibly do case 2 for row 2, you might have to return to row 1. If you use case 2 for some of the roots, then you forget about it forever. But until then, you might still have to return to it. Because, for example, if you focus very closely to row 2, you might not see good points because tau 1 is much bigger than tau 2. Okay. Okay, so this proves the analog of Davenport's theorem for binary anyc forms. We don't have spectral gaps. We always have extremal, almost extremal lattices. Okay, now how do we fill the whole interval? So we can't do exactly what we did for the binary cubic case, which was to restrict to curves that isolate the root row 1 and fix row 2, row 3. We don't have enough dimensions to fix everything. So the family of lattices we play with in this case is diagonal perturbations. And in order for the local stability to work, which is the reason we wanted to find almost extremal lattices with good properties, we work at lattices of the form almost extremal lattice composed with this family of diagonal perturbations. And I won't go too much into the details because it's somehow exactly what happened for the binary cubic case, but with many, many more computations. But using the exact same strategies, you fill the whole spectral interval modulo a set of measure 0.
Yeah, how big do you have to take theta? I mean, this is diagonal action. Do you have to sort of flow until something happens, or?
It's still very
small.
It's very localized. You can go.
Okay, so it's just fattening.
Yeah. Oh, it's the fattening comes in at the third step. Here's just a curve. The fattening comes in to exclude the measure 0. So how do we get rid of the measure 0? So in the binary cubic case, what happened is that we were able to use Steinhaus theorem. But here our variables are not independent. So you can use Steinhaus as long as your variables are independent. You have row 1, row 2, or 3, they can be whatever. But row 4 is not independent as long as you have at least 4 degrees. And Steinhaus stops working when you don't have independent because, yeah, you can take A to be the real numbers, and you can take A prime, the subset of R squared, to be X and Y, such that X minus Y is an irrational. Say. In this case, the projection on each of the 2 coordinates is everything. We have a full density, full measure phenomena, but still this function it doesn't cover an interval, which is exactly what happens here. You can't use Steinhaus or any of the theorems or any of these projection theorems if you don't have independence of the variables. And so the trick is to introduce a certain fattening of the diagonal flow. As follows. So along these orbits, the flow, the binary form has this form. So essentially you just introduce a theta there. what you have to do is a very convoluted shifted version of the density increment that I just described. You have to introduce a variable tau3 and tau4. And it's another version of the structure theorem to prove the following, that if theta is very close to a convergent, just like before, Pn over Qn, and U is very close to this product right here. This product would be essentially theta is equal to 1, and we forget about the x and the y. What happens is that we can find some t such that the projection of the roots under Mobius transformations of t are very good. Again, they're in the epsilon. And this number right here is in the spectrum. But now u is a variable. Here theta is fixed, Qn is fixed, u is a variable inside a neighborhood of this number. So you find very, very small intervals, and by taking this n to infinity and theta in the flow, this is a thickening of the flow, you fill the whole spectral interval. Okay, and in the 2 or 3 minutes that I have left, I want to advertise some open questions in the subject. Okay, so the first one is what happens with a rational spectrum. Now, what is the rational spectrum? We take the base node spectrum just as we defined it, but we restrict it only to lattices such that P adjoined, P composed with a matrix representing this lattice is a scalar multiple of a rational form, not a rational form. Scalar multiple of a rational form. What is the spectrum there? So, in other sense, maybe an easier example would
If you were in cubic case,
yeah, maybe we should.
one invariant of the reals, except the sign, then you're getting all rational binary.
Right. So the question is,
Rational coefficients.
Yeah.
Very clean question that you ask.
yeah. So if you take integer binary cubic forms,
Yeah.
what is the smallest integers they represent over the 4th root of the discriminant? This is an arithmetic statistics question, probably. We know that they have to represent something before they reach 4th square root of discriminant over 23. This was proved by Mordell. But is it true? Also, the rational spectrum, by definition, is a countable set, so we want to take its closure to study it. But is it true that the closure of the rational spectrum is the spectrum itself? I should say that in the case of binary quadratic forms indefinite, this is not true. They look very close, but the closure of the rational spectrum becomes a Lagrange spectrum, which is different than the Markoff spectrum. So I think this is a very interesting question to study. And another interesting question is, even though we understand now that everything is an interval, I have no idea what this constance MP could be. This is probably a very hard project for every binary form to understand MP. But I also have no idea what the extremal lattices look like. It should be the case that the roots of the extremal lattices have the Diophantine exponent too, but I don't even know that. The whole density argument was to approximate it by forms that do. What we know is that they can't have Diophantine exponent larger than n, but there might, for some reason, be some form that has an extremal lattice of Diophantine exponent exactly n, which is the barrier. So, some sense, an extremal lattice such that the lambda 1 eigenvalue is not a minimum, but it's actually an infinite. It didn't happen in any of the binary cubic case or in any cases that I discussed, but I don't know if it doesn't happen in general. So that would be an interesting. And I think I'm going to end my talk right here.
Any questions?
The extremal lattices are unique.
Unique. So
How do they change?
in the case of Mordell, he proves that. The binary cubic case, they are unique up to, you know, the S3 action as well to Z action and stuff like that. In the general case, I do not know. I don't even have a single case, even for X fourth minus Y fourth, for example, something simple. Sounds like that. I don't know what the external lattices look like.
I mean, for the rational, do you know anything? I mean, is it possible that it's rigid, meaning that the I go of all binary, just for the cubic case.
Well,
Binary cubics, I look at the integer ordinates. I ask, does this minimum, and I divide by the direct power of the discriminant. Is the smallest guy, can you construct an infinite sequence of binary cubic forms where the smallest guy is growing like it is in the Markoff? I would imagine yes.
somehow, if I translate this question into
It's enough.
minimal representations of binary forms, I don't believe it. But if I translate it into continued fractions, I do believe it. So I don't understand.
Yeah.
Because the question is equivalent to, you take an algebraic integer and you want to do the following. You want to shift the coefficient of the minimizing polynomial by a little bit so that you don't change the
No, but the rationality and the discriminant, although the point here is the rational guys are dense, but their discriminants get big. So the rational points maybe behave very differently here, which is not impossible. You've shown that you use measure theory, then you use Steinhaus to get everything. I just say it's an interesting question, what's happening with the rational. It's not clear to me. I mean, I think there's a theorem, maybe people know, maybe they don't know, that Schmidt wrote a paper where he shows that the Tour theorem, which says that there are only finitely many solutions, he gives a bound, which is that the number of solutions to f of x, y, the x and y are arbitrarily large, right? So you fix your binary cubic form, say.
Yeah.
And the number of solutions to f of x, y equals k is finite, that's Tour. The number of solutions to f of x, y up to equals k is mostly zero. So the number of solutions up to the discriminant to the power we're talking about is bounded or something. In other words, he extends it to small values of f of x, y, which seems to me like it should be giving us a hint as to what should be true. In other words, he's studying small values of f of x, y, and not just is it equal to a fixed number.
Are there any more questions? No, let's thank yours one more time.